All right, welcome back to another video in our series on Newtonian dynamics. Today we're going to be talking about an extension of the concepts that we talked about in the last video. So if you'll recall, in our last video we talked about Newton's second law and how we can relate the forces to a mass of an object times the time derivative of its velocity. One thing that we should note and that we didn't mention in the last video is when we have this equation, really we need to express this in terms of inertial quantities. So what that means is that force is really the mass times that inertial acceleration. And really all we're saying when we say an inertial acceleration is some sort of reference frame that is moving at constant velocity. So say, for example, we're throwing a ball on Earth. So that ball is going to be moving through space, and that ground that we have is an inertial reference frame. So it's not moving with respect to the motion of this ball. So we typically write our inertial reference frames as either I or E, which is what you'll see for the rest of our videos here. So what we want to do is always write our Newton's second law in terms of inertial accelerations. But what we often run into is a lot of the times our sensors and other things are not going to be in this inertial frame. I'll give you an example with our rocket modeling. So say we have our rocket here, and we have some sensor on it, say something like an accelerometer. So if we have an accelerometer here in the nose, our accelerometer is going to be measuring accelerations, but it's going to be sensing those accelerations with respect to the rocket. So let's say this rocket is following some path through space. This accelerometer is not going to be measuring inertial accelerations. It's going to be measuring accelerations with respect to the motion of the rocket. So it's really important for us to be able to take these accelerations and other quantities that are non-inertial and convert those into inertial frames. So in this video, we're going to be talking through how we can do that. I'll start with a simple example. Let's say we have a spinning disk here, and we have a bug that's on this disk. So this bug is kind of crawling along this disk, and he's moving radially outwards over time. And what we can do is say that this bug's distance along the disk is x, and we can call this center point O, and the position of the bug is P. So what we'll want to do is write this in terms of a frame with respect to the bug and also an inertially fixed frame. So I'll go through and draw some reference frames, and then we'll start from there. All right, so now I've gone and I've drawn some reference frames here. We can see I've drawn this E frame, which is our inertially fixed reference frame that we were talking about before. So if we think about this disk maybe rotating on top of a table, we can think about this E frame being embedded in the table itself. I've also drawn this B frame, which is drawn with respect to the motion of this disk. And our bug is crawling along this B1 direction. So we can go ahead and think about the relationship between this E frame and the B frame. At some arbitrary time, this B frame might be rotated with respect to this E frame. So we can go ahead and express what those B frame components look like in terms of the E frame. And to do that, we'll just use some simple trigonometry. We can say that this B1 vector, for example, is just going to be cosine theta E1 plus sine theta E2. And we can do the same for this B2 component. We can say that B2 is simply going to be negative sine theta E1 plus cosine theta E2. And in general, we can do this for any set of orthogonal vectors. The next thing that we're going to talk about is how we can use these relationships to write the velocity of the bug in the inertial frame, which is ultimately what we're trying to do so we can apply Newton's laws. So to do that, let's go ahead and define a few things. We'll say the distance of this bug from the point O to point P is x. And so we can write this vector from the origin to the bug. We'll call that ROP. So we'll say that is this R vector from O to P. And we can say that is just going to be x times that b1 direction. And then we'll also define the velocity of this bug going outwards is just v. So the first thing that we want to do is think about how this bug is moving in the B frame. So this B frame is rotating and the bug is walking outwards. In the inertial frame, this motion is going to look pretty complicated. So this bug is going to be walking outwards, and as he walks outwards, there's going to be some spiraling due to this rotation of the disk. But when we think about this in the B frame, this velocity is pretty simple. The bug is just moving directly outwards. So we can think about just taking this derivative with respect to the B frame of this position vector. And that's going to give us x dot times b1. And we've said that this x dot is just this velocity v, so we can call that v b1. So now what we're going to do is take into consideration this angular rotation effect. And the way that we can kind of go about that is think of other examples of rotation that we've seen in basic mechanics. So let's take, for example, our angular momentum, which we'll call h. We know that is r cross mv. And say, for example, our torque, another similar rotational quantity, is just r cross f. So we can see in both of these instances, we have this cross product here that determines how things act when they're rotated. So we can do the same thing here, and we can say that we should have some component of this velocity that acts in this orthogonal b2 direction due to this angular velocity omega. So let's go ahead and write an expression for that. We can say we have this omega of b with respect to e, which, by the way, this notation just means this is the omega of the body frame with respect to this inertial frame. And we'll cross that with our ROP vector. And what that's going to give us, if we calculate this out, this omega of b with respect to the e frame, using the right-hand rule, is just going to be in the b3 direction. So that will be omega b3 crossed with this x times b1. And if we go ahead and calculate this, that is simply going to give us omega x times b2. And if we think about this, that is what we would expect our result to be. As this bug moves outwards, we should expect this velocity is going to increase in magnitude as the bug gets closer to the edge. We also know that this should be acting in the positive b2 direction, so that gives us some confidence that this result is correct. So ultimately what we'll do to finish the construction of this is take this velocity with the B frame and add it to this velocity due to the rotation, and that will give us the relationship between the inertial frame and this body frame. So we'll say that the inertial time derivative of this ROP vector is simply going to be this body frame derivative of ROP plus this omega of B with respect to E crossed with ROP. And for this example, we can go ahead and plug in all those components, and we can see that we're going to get this inertial derivative of ROP is simply going to be this term, which we said was V times B1, plus this term, which we said was omega x B2. And of course, this is where it might be useful to have these trigonometric relationships where we can go ahead and express this in an inertial frame. And you can see that because we have this relationship here, ultimately we can express this derivative of ROP completely in terms of inertial quantities. So this important expression is what we call derivative transport theorem. Sometimes you might hear it called the BKE, or basic kinematic equation, but this is the governing equation that tells us how we can relate a body frame acceleration or a body frame quantity to its inertial derivative. So that's it for this video. In some future videos, we'll use this relationship in things like attitude dynamics and understanding sensors and see how we can use those relationships.